Here, let's start with the details of this section, these chapters. This chapter about the deformation of the shaft and under torsions. And the first one, we will take a look at the assumptions that help us to build up a appropriate mathematical model for describing the deformed shaft. And then we introduce a terminology called the angle of twist. And then from there, we will go over how to calculate the shear strength and shear stress. So here I try to come up with some a schematic diagram to better explain the assumptions we're going to make. Basically, when we study torsion of the shaft, we assume the shaft is uniform. So that means its radius, let's say C, basically that is the constant radius throughout the whole shaft. And then here, if we have applied the torsion here, and due to equilibrium, you should be able to find out on the other side the torsion is T here. Okay. And then let's take a look at the further details about the assumptions we're going to make. The first assumption is this: order point when on the cross section. For example, we consider this cross section. Order point, material point, once deformed, the material point will undergoing rigid body rotation. This is saying, for example, if this point originally on the undeformed configuration located here, then due to the application of the torsion, this point will follow the parameters of the same radius and move to here. So moving from A to A prime. And for example, we look at this cross section here. And again, this is the point on his original undeformed place. And again, due to the application of the torsion throughout the whole shaft, in this cross section, this point will be displaced to here due to the application of the torsion. And again, such a displacement is to follow the same rigid body rotation basically follow the same the parameter of the same radius here. Okay, and this point here, for example, if copy from our textbook, it's assuming this side is clamped to the wall, so basically here is no movement here. Okay, so that's assumption one: rigid body rotations. Rigid body rotation of the cross section for describing the displacement of the point. Okay. Then we're going to introduce the second assumption. The second assumption is this. Before we're doing that, let me introduce a few parameters here. So say the distance of this section to the wall, let me say that is lowercase l, and the distance from the free end to that wall, basically that is the length of the shaft, and let me call it capital L. And here A move to A prime, so that is swept by an angle. Let me call the uppercase phi, and corresponding in this cross section, let me call the lowercase phi here. Okay, so with all the symbols ready, the second assumption is this angle being swept due to rigid body rotations on the cross section basically is proportional to the distance of the cross section to the wall here. Okay, so that is the second assumption. Basically, you could imagine if this end is fixed against the wall, so basically this cross section doesn't move, doesn't rotate. Any cross section, circular cross section taken from the circular shaft, any circular cross section basically under the application of the torsion will be undergoing rigid body rotations that around the center here. And the amount of the rigid body rotations amount of the rigid body rotation that accounts for the displacement of the material point. Okay, the amount of the rigid body rotation of a cross section basically is proportional to how far they distant away from the wall here. So the farther away from the wall, the more amount, more quantitatively, they rotate. Rigid body rotation have more. Okay. You may wonder why we want to make such two assumptions. Basically, the two assumptions can be proved that is actually is a fact. They both are fact. Okay, they are the fact corresponding to circular shaft. Okay, so basically the two assumptions, we can prove as the fact for circular shaft. Okay, and here in this class we won't have time to learn how to prove it, but here we simply take it. Okay, so we simply take this knowledge. Basically, that is true. That is true for circular shaft. And why we want to study the circular shaft? Because circular shaft give us such a simple model, and that can be complicated to reflect, to capture all the features of the shaft under torsions. Okay, so other geometric can be, for example, elliptic shaft, and can be, say, rectangular shaft. Okay, and other shaft, the shafts other than circular shaft, such assumptions, say assumption 2 will be held, so assumption 1 wouldn't be anymore for the other shaft. And why we study the circular shaft? Because due to the two facts, and that one will allow us to prevent a little bit bothersome or complicated phenomena called warpage. Okay, the warpage basically is indicating displacement of any material point in the axial direction. So for circular shaft, we know right now, due to the fact all the point will be displaced in plane, in the circular cross-sectional plane. They won't have any chance, they won't be able to displace in out of plane. Okay, so any displacement causing in the outer plane of the cross-section or in the axial direction, that called warpage. Warpage actually is a little bit more complicated phenomena, and that will involve quite a bit calculations. So as a fundamental mechanics material, we have no time to study the warpage. So that is the reason here we take the circular shaft as our model. That will keep our model as simple as possible, but also be able to capture all the major features. Okay, so let's move on to get more details how to quantify the calculations in more details here. Based upon the two assumptions, and then here is our shaft. Okay, so let me get the given information. So for example, if this is a solid shaft and have a radius c, and this shaft has the length L. Okay, and so that is a given information. And then for example, here we still assume follow up our textbook. This is a wall. Okay, one end fixed to the wall, and the other end we applied torsion. Okay, to make our formulation more generic, more general, and how about that? And let me take a core material that is radius of R. Basically, R is parameters. R can be from 0 to C. Okay, if this will be the hollow shaft, then the hollow shaft basically is something like this. Then the domain of R will be from, say, C of the inner radius to the CO outer radius. Okay, so depends on the shape. Basically here R is parametric. So for simplicity here, let's assume that is the solid. Okay. So with this, consider this free body diagram here, and again this one again we fix against the wall here. And then here let us starting the first one to identify what is the shear strength. Okay, and if you remember the chapter 1, our definitions, the shear strength is defined as the change in angle of a patch. Okay, so if this is the undeformed, then after deformations, then using this the dashed line. Okay, if that is a deformed shape, basically this is what we defined as the shear strength. Okay. Now keep this concept in mind, see how much we can do about here. So here, this line, this point, or the point on this line, along this line here, okay, that is corresponding to where the torsion has not applied yet. When torsion applied, this straight line basically displays to this straight line here. Okay, and then here, if initially let me make a patch that attached to undeformed. Okay, and then let me move that drawing to here. Then when the torsion is applied, then you can see this point basically move to here. Okay, and then the corresponding, so that point, this point move to here, and then this point basically will follow to the rigid body rotation along the parameters will be moved to here. So this is the on the same section, this point will be moved to here. Okay, so let me link. So that is the deformed shape. And why the 2 point doesn't move? Because the 2 point is here that attached to the wall. Okay, so compared to this definition, the angle, change in angle, give us the definition of the shear strength. So from here, are you able to right away to tell that is the change in angle of the patch? So basically, this is our shear strength. Okay. So this is the shear strength, and then basically that is the function of R. Okay, function of R. So here, let me do the limits, remind us. There's a function of R here. Okay, keep these things in mind. So basically, right now we identify the shear strength. Basically, is the angle measured by this. Okay, and then we further to get further more information is this. Let me denote this angle here. Okay, that is capital Phi, and this small angle here, the angle to denoting the rigid body rotation of this cross section. Let me use the lowercase phi here. And from here, this is the distance of this section from the wall, and that is the distance of this section and free end from the wall here. So from here, are you able to see, if we look at this distance, that is equal to R times Phi. This is an arc belonging to part of this circle, so that's R times Phi here. But also, this is also can look at as the portions of this big triangle. So from there, you should be able to see that is R times gamma. Okay, again, gamma is a function of R. It's not that important. In a similar way, we look at this distance here. Okay, that one basically again is part of the arc length of this circle. So basically that is equal to the radius, which is equal to R times Phi. Okay, let me change color back to here. So that is R again right now for this yellow one, so that is r times lowercase v. And again this portion, if you look at this triangle again, so that one equal to L times gamma. Okay, gamma is r. So by doing so, so you should be able to see that one equal to so from here you should be able to see, say basically that is v divided by this one equal to L over L. So that is our back to our assumption 2 here. Okay, so basically that repeated information here. And then more importantly, I want to derive from here. So that is the information I want to have a second derivation. So starting from here, we can see the gamma, and that's a function of r, simply equal to r v divided by L. So this is the shear strain. By multiply the shear strain with the rigidity modulus, and that is given as the function, that is the shear stress. Okay, so shear stress is a function of r, basically equal to g r v divided by L. Okay, and then from here, so basically here we can see that come up with quite a bit of information here. So here we would look at this one, the tau, that is the functions. The shear stress is a function of r. What this mean? Basically this meaning is this: in the cross section, for example, let me pick these cross sections here. So in a cross sections, this is the center here. The shear stress is a function of r. When r equal to 0, shear stress equal to 0. When r equal to the radius c, the r equal to the maximum. So basically, schematically, you can see the shear stress is in linear distributions like this. At this radius, the magnitude is that. At this radius, the magnitude is that one. So the radius equal to c here. So the maximum here, we can see the maximum basically equal to happened at the outer parameter here. So from here, we can see for a shaft is under pure torsion, the maximum shear stress is always on its outer surface. The minimum will be at the center for solid, or if for hollow shaft, the minimum will be at the inner core there. Okay. So at any distance, and say this distance is r, then tau equal to this one here. Okay. And so that is kind of the more quantitative, but not really answer our questions here. Our question is this: although right now we schematically know the distribution of the shear stress is like this one here, but now the question right now still remain is this: we still don't know what is this one here. Okay, we want to answer these questions. To answer that questions, maybe we can try is to translate the information to the this cross section here. Okay, so again, that is the cross section we made. Let me continue using that cross section here. So basically, right now I take this cross section here. Okay, and for this cross section, basically we can, that cross section is at L equal to L. Okay. And so that means basically tau is a function of r, and that is g. We take this template and r. Okay, and at this cross sections, and this angle corresponding is become this. Okay, and then when L equal to L, so basically replace L by capital L. So simply we take this as a template and replace the corresponding information at the right position there. Okay, so something like this one. So we move on to have more space to allow us to work on. So again, right now I pick this cross section here, and let me draw the distribution of the stress on this cross section here. Okay, So basically here at any distance r, the doesn't they can be okay. So the shear stress is a function of r equal to g. What is that? So g r phi over L. Okay, so basically that is the due to the application of the torsions. So that is our phi here. Okay, that is A, and rigid body rotation to A prime here. Okay, so that's a torsion here. And so from here, usually the people define the phi as called the angle of twist. So given this shaft is on clamped on one side, at the free end, we define this angle of the rigid body rotation. We define as the angle of twist, and angle of twist usually can be easily measured because that located at the free end here. So here I introduce the angle of the twist here. So now we're back to here. So here we have the informations, and so L usually is the dimension of the shaft. We know we can measure it. G is the material properties, and they are given. So here we still unknown is what is this one? What is the angle of the twist for these conditions? We want to answer this question here. This question can be answered by this. So if you would consider this stress applied to a small area dA, so the stress, and let me drop off the function of r, okay, and by keeping on this a function of r. So stress multiplied with small area give us a small force, and such a small force multiplied with the arm distance, so basically that gives us a small moment. Such a small moment is being contributed by so many small patches everywhere around the cross section. So basically we take the integral about the cross sections area, and the whole small moment together should be in equilibrium with t. Okay, so that is here we have taken the equilibrium equations in the moment and to make this one. So let me introduce what is tau here. So we simply introduce tau to this equation here. So let me rearrange r times g r phi L dA equal to t, and then here there's a constant, a few constant that I can take out. G is constant and phi is unknown, but that is constant. L is constant, so let me take out the constant out of the integration. G phi L, and on the cross-sectional area, and r squared dA, okay, equal to t. And from here, this one, if you remember from your statics, basically this is we call the polar moment of inertia of these cross sections about its center. Okay, so basically this integral has meaning like this, and in our textbook we define as a j. And whenever given the j, so for example for a solid shaft of radius c, okay, the radius c, the j equal to pi over 2c to the 4th power. And for hollow shaft, okay, for hollow shaft that has the outer radius CO, the inner radius CI, then j equal to pi over 2 and CO to the 4th minus CI to the 4th here. Okay, so we back to our problem statement here. So from here we can see basically here phi equal to, with the introduction of the j here, phi equal to TL over GJ. So by doing this, we have solved this one. And once phi is solved, and that is the angle of the twist, whenever we are given the torsions, we know the dimension L, we know the material properties, we know the geometry. Basically, this is determined. So we're back to here. So tau, once we know this one, then we can see what is tau. So basically, tau equal to G times R L. And then we introduce phi here. So basically, phi is T L over Gj. So here we do a little bit cancellations here. So L canceled, and then G canceled. Okay, so basically tau as a function of R equal to T R over J. So this is the equation here. Okay, tau equal to TR over J. And once we know the applied the torsion, we know the geometry J, just like this one here. Okay, then if you determine which locations you want to calculate the stress, you determine UR. So tau equal to this one. So basically from here you can see the maximum is occurred at R equal to the outer radius. Okay, C, basically the outer surface here. And where is the minimum? Minimum for solid shaft, that can be 0 at the center. The minimum for hollow shaft basically happened in the inner core here. That is non-zero, but that is the minimum. Okay, so that pretty much introduced all the needed equations for this chapter. That's a fundamental one. So here is the detailed kind of layout, our description from our textbook, and that pretty much captured all these things I've been talk about in the previous 3 slides, and you can go over in details by yourself and to refresh the concept one more time. Okay, so that pretty much have everything we needed here, and then yeah, so quite a bit in detail. That's it. Okay.